Good afternoon, ladies and gentlemen. We all like good food. Good food which is tasty, nutritious and healthy. And as the keynote speaker already said, we need microbes to make good food. The cheese in a salad has been made by microorganisms, as well as the vinegar used to flavor the salad. But microorganisms can also spoil our food. And when they are present in high amounts, we can smell it and also taste it. So basically, when we consume food, we also consume a lot of microorganisms. But also pathogens can be present in food, and pathogens can make us ill. In fact, 1 in 6 persons per year get sick by foodborne pathogens. And most of these diseases are mild and people recover quickly. But you might also recall the EA crisis from a couple of years ago, where hundreds of people got sick and also people died. And these outbreaks are rare, but the impact is huge. But when you take into account that in Holland, with 17 million of people, we consume 3 meals a day, then in most of the cases people do not get sick. And far most of the meals we consume are safe to eat. So pathogens in food can make us sick. But not all pathogens in food do make us sick. And that's because when a pathogen is in food, it also has been able to survive in soil and on raw food materials. And only the fittest one will survive from soil to man. And this brings me to the key question I'm working on, I'm going to talk about today. How can pathogens survive along the food production chain? In soil, they might grow, but when we process food, they will be inactivated. The ones which survive the process treatment, they will grow in our food when we store our food. Pathogens will be also inactivated when we eat our food because of the low pH of our stomach. And only the fittest pathogen will finally reach the human host in sufficient amount to make us ill. And we all know that general hygiene is important to prevent transmission from pathogens from person to person. But only the one which survives the food processing chain will reach the human host. And I want to predict the path of the pathogen. So which one will finally reach the human host? So I'm a food microbiologist, but actually I'm a food detective, predicting the path of the pathogen. So what is my approach to understand the behavior of foodborne pathogens along the food production chain? For that, I need big data on different levels, from genome level to ecosystem level. Information on molecular level gives me the fingerprint of a microbe. And this allows me to understand why single cells behave differently, and therefore how a population as a whole behave. Microorganisms are present in ecosystems, like in soil and in food, and the conditions in these environments are not fixed, they vary in time. And I want to predict the behavior of pathogens in these ecosystems. So the theme of today is big data, and how I'm dealing, or how our field is dealing with big data. First of all, for identification. How can we prove that the isolates from the food have caused the disease? Now for that, we compare the genetic fingerprint of the food isolate with the isolate from the patient. And when there is a perfect match, and the fingerprint is the same, then we can prove, yes, indeed, the food isolate have caused the disease. So identification is important to prove a disease, but we want to prevent illnesses. And therefore we have to predict the behavior along the food production chain. So as you know now, I want to predict the behavior of pathogens along the food chain. But realistic prediction is not easy. And that's because microorganisms are not all the same. You and me are different, and the same holds true for microorganisms. And I want to understand why they are different. Why are pathogens different? To understand that, why they are different, I isolate pathogens from different sources, from the soil, from the food production environment, from food, and I also get clinical isolates. And when I have these different strains, I study them on different levels. Information on molecular level gives me the fingerprint of the microbes, and I compare millions of base pair. Also, I study their behavior to understand in which circumstances they do well. Which strain, for example, is heat resistant, and which one does grow well in the fridge. And then I can combine these two sources of information to find genetic biomarkers for heat resistance, or a biomarker for good growth at low temperature. And when I understand variability, I can also predict variability when they grow in the food chain or when they are inactivated by food processing. So in summary, pathogens are different. There's another level of complexity, and that's single-cell diversity. We have thought for many years that when cells are copying themselves, when they're multiplying, the copies of the cells are exactly the same. But it is not the case when we have millions of cells, because then a subpopulation is different from the majority of the population. And then you can ask the question, is this a problem? It can be. Assume we want to heat treat a product, and you assume that all the cells are exactly the same, and you think you will have a linear inactivation. However, when a subpopulation is different from the majority, by this heat treatment, you will select for this subpopulation. And we're talking about just a few out of millions. And then again, you can ask the question, is this a problem? It can be when this subpopulation are good growers and then can become troublemakers later on in the food production chain. So we have to study these few cells out of millions. And how can we do that? For that, we have a high-throughput device in our laboratory, the flow cytometer and a cell sorter, allowing us to analyze 90,000 cells per second. All these cells are passing a laser, and depending on the characteristic, they are sorted in different tubes, allowing us to select the subpopulation from the majority of the population. And then we can study the single cells from this subpopulation to see whether they can become the troublemakers in the food production chain. So I want to predict the behavior of pathogens along the food chain. But realistic prediction is not black and white, which makes my life as food detective also challenging. Because microbes are different, and therefore I need big data on genomes, on how they behave. I have to work with many strains. I also have to work on single cell level. And by combining these big data sets, I can realistically predict the behavior of pathogens along the food production chain. This is a situation you see we do not want to have, because people still get sick. But when we can predict the behavior of pathogens along the food chain, we know whether and when in the chain we can intervene to sufficiently kill pathogens, to reduce foodborne illnesses. So by working from molecule to management, we can optimize food safety. And food safety is important because we all want to have good food we like to eat and which is safe to eat. Bon appetit en eet smakelijk.